In this video, we're going to look at series and their convergence. So the idea is going to be summing up something. So we're going to add up a bunch of terms. The notation for the summation is usually done with a capital sigma. And if I start with terms that we call a sub n, if I count from n equals 1 to 4, I'm adding up 4 terms. That is the notation for any sum. Well, an infinite series is an infinite summation of terms. So we're going to sum up from n equals 1 to infinity a bunch of different terms. So we add these things up, and if we think about A1, A2, A3, so on and so forth, as being the terms in a sequence, then an infinite series can be thought of as the sum of a sequence. Now, the big question is, can we add this up? Does it make sense to add up an infinite number of terms? When we talk about adding up 4 terms, it's pretty straightforward. I just add up the 4 terms. Once I get to the 4th term, I stop. With an infinite summation, well, if I was to do this manually, I would never stop adding. And therefore, we try to develop some clever tools to figure out when we can add this up, when it's going to add up to infinity, when we're going to get other weird answers where it can't add up. So the first tool that we look at is the tool of partial sums. The partial sums are the sums of the first few terms in the infinite series. So we have this infinite series, which is a sum of infinitely many terms. And what we look at is the partial sums. That's the sum of the S1 is just the first term by itself. S2 is the sum of the first 2 terms. S3 is the sum of the first 3 terms. S4 would be the sum of the first 4 terms. Sn is the sum of the first n terms. So we look at one tool we can use is looking at the partial sums and seeing what those are headed to, because the partial sums themselves will form a sequence and we can find the limit of that sequence. And that's what we look at. The infinite series, the infinite summation from, let's say, n equals 1 to infinity of terms a sub n converges to a number, we'll call it S, if the limit of the partial sums is S. So if the limit of the partial sums is S, then we say that the infinite series adds up to S. And on the other hand, if those partial sums diverge, so if the sequence of partial sums diverges, then we say this infinite series also diverges. So the infinite series converges if it adds up to a real number. And the way we calculate if it adds up to a real number is we create a sequence of partial sums and we see if that sequence converges to some real number. If that sequence of partial sums diverges, then we say the infinite series diverges. So converges when the limit is equal to some number, diverges if the partial sums diverge as a sequence. Let's do an example to show what's going on. Let's take the infinite series, which sums up 1 over 2 to the nth power, and we start our count at 1 and we go off to infinity. What I like to do is I typically like to write out the first few terms of what's going on. So basically 2 to the n, that's powers of 2. If you start your count at 1, we get 1 over 2 to the first, which is 1/2. If I then go to my next term, that's a n equals 2. 1 over 2 squared is 1/4. And then I get 1/8, 1/16, 1 over 32, 1 over 64, and then 1 over 128, and so on and so forth. 256, 1 over 256, excuse me. And you can keep going on and on and on forever. Then I start looking at partial sums. The first partial sum obviously is 1/2. The second partial sum is the sum of the first two terms. That's going to be 1/2 plus 1/4. 1/2 plus 1/4 adds to 3/4. I'm going to keep these as fractions for demonstration purposes. It turns out that when you write this as a fraction, it'll become obvious what the partial sums go to. When I take 1/2 plus 1/4, that's 3/4, plus an eighth, I'm going to get 7/8 as a fraction. S4, basically notice that this is like 7/8 plus a 16th. So if I add a 16th to this, I can just write double the top and bottom. So that'll be 14 over 16 plus a 16th. That's 15 over 16. And then S5 is going to be, well, take 15 over 16. That's the sum of the first four. And then add 1 over 32. You're going to get 31 over 32. And S6 take that 31 over 32 plus a 1 over 64, you get 63 over 64. So here are the first few partial sums. Now, hopefully we see a pattern. Notice that the denominator is always 2 to the nth power. So 2 to the first, 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth. And then the numerator is always 1 less than that. So the partial sums in general always look like a fraction 2 to the n minus 1 in the numerator and 2 to the n in the denominator. It's pretty obvious. Well, maybe it's not obvious, but you can use algebra to show that the limit of these partial sums as n goes to infinity is going to go to 1. So this limit of 2 to the n minus 1 over 2 to the n spoke. Maybe that's obvious for some people. If it's not obvious for you, then what you could do is you could say this is the indeterminate form infinity over infinity. So you could apply L'Hopital's rule if it's not super obvious. And L'Hopital's rule would say derivative of the top is 2 to the n times natural log of 2. Derivative of the bottom is also 2 to the n times the natural log of 2. The minus 1 would go away. And that's pretty obviously always 1 when you do an algebraic simplification. So obviously, I wrote this in long form, but there's a lot of different ways you can write this, a lot of different ways you can keep track of what's going on. We have this pattern, S sub n is equal to 2 to the n minus 1 over 2 to the n. The limit of that is 1. So that means the limits of this sequence, this partial sums sequence that I've created, is equal to 1. And what we say is, therefore, this summation is actually equal to 1. So we say this infinite summation is equal to 1. Or, in other words, it converges to 1. So the summation, this infinite summation, is equal to 1, or it converges to 1 is the language we use. Hopefully that makes sense. So that's the overall idea. Obviously, sometimes partial sums are easy to get and easy to see what's going on. In this case, my simplification was pretty straightforward. I just left things as fractions and then I could see it. Other times it might be more difficult to see, and we'll see some examples of those. Notice how we're saying a sum, it's pretty kind of mind-blowing that we're actually determining something that I can't do by hand. I can't actually add up infinitely many terms by hand. But with some logic, we can say that the sum of infinitely many terms converges to 1. By the way, this one has an actual geometric visualization that's kind of nice. Not all of them will have a geometric visualization, but this is how it goes. If we have a square, a 1 unit by 1 unit square, so it could be 1 foot by 1 foot, or 1 meter by 1 meter, or 1 inch by 1 inch, whatever the unit size is, then the area of that square is 1 square unit. What I can do is I can start cutting sections in half. So if I cut this in half, I'll do the best I can to cut in approximately a half. then this half down here is going to be a half of a unit. Let's actually change that up. So that's a half of the actual square. And then if I take another cut, let's take this to there. That will be a quarter. And then if I take another cut, that'll be an eighth. And you can see we can start doing this infinitely many times. Let's change that up. And we keep getting we keep cutting the remaining section in half. And we start to fill up the entirety of the area of the square. Now, at a certain point, we have to, I'll stop using different colors, but at a certain point, what's going to happen is all of these half cuts get so small that my computer or the look is not gonna do very well, but it's not gonna look real nice. But I think we get the point. Just keep cutting in half. So we get a half plus a quarter plus an eighth plus a 16th plus 1 over 32 plus 1 over 64 plus 1 over 128. And then we do a plus 1 over 256. And then keep cutting in half and half and half and half and half again, over and over and over again. And that eventually, well, essentially if you take the infinitely many cuts, it should fill up the square, theoretically. And that shows you that 1/2 plus 1/4 plus 1/8 plus 1/16 should actually add up to 1 because it should fill that square up. So while we can't manually add up infinitely many numbers, we actually know that when we add up infinitely many numbers, again, the summation converges to 1. Not all infinite series are going to have nice geometric visualizations. In fact, most don't. And a lot of them will have nice partial sums, but again, there will be some that don't either. Let's do another one. Let's take a second example. This is an infinite series where we're summing up from n equals 1 to infinity 0.4. All right. Now, if I don't see any n going on here, what this means is I just take 0.4 for the first term, and the second term is also 0.4, and the third term is also 0.4, and the fourth term is also 0.4, and the fifth term is also 0.4, and so on and so forth. We're basically just adding up 0.4 infinitely many times. If you think about what, I won't do as many in this case, but The first partial sum, therefore, would just be 0.4. The second partial sum would be 0.4 plus another 0.4, which is 0.8. The third partial sum is going to be 3.4s added together, which gives you 1.2. The fourth partial sum is 4.4s added together. That's 1.6. The fifth partial sum is going to be 2.0. The sixth partial sum is going to be 2.4. Again, we're just adding 0.4 over and over and over. And now I can see, hopefully, that the infinite pattern that we're getting for the partial sums is just 0.4 times n. We're getting n copies of 0.4 when I add this up. As I look at this, that means the limit of the partial sums as n goes to infinity is the same as the limit of 0.4 times n, which is going to actually be infinity because these partial sums just keep growing, or you could say as n goes to infinity, 0.4 times n is also going to infinity. That means this original summation, well, we say that this original summation diverges or diverges to infinity. And that's it. So the limit of the partial sums diverges. Again, these partial sums I'm looking at as a sequence of numbers. So I'm looking at the partial sums as a sequence of numbers. This is the function that gives you the terms in the sequence. So the limit of the sequence of partial sums is an infinite. Therefore, the limit of that sequence diverges. Therefore, the summation that I was looking at also diverges. Again, in this case, some people would say just diverges. That's what I tend to say. Other times you'll see people say that this infinite series diverges to infinity. Now you can kind of see what's happening. As you keep adding 0.4, your terms are never going to zero. The individual terms are never getting down to zero. So my partial sum is just going to keep growing and grow. My partial sums are going to keep growing and growing and growing. And you can see that anytime these terms don't get closer to zero, when we add them up, they're going to go off to infinity. In my first example, the terms did get closer to zero. The individual terms that I was adding up, I misspoke, but the individual terms that I'm adding up, as n goes to infinity, these individual terms are going towards zero. The fractions that I'm adding are going towards zero. So the partial sums had an opportunity to converge. If the individual terms never get close to zero, then the partial sums never have an opportunity to converge. And that's going to be our next result. This result is called the divergence rule. It says if we're adding up a bunch of terms, if the terms, the a sub n's, don't go to zero, then the infinite summation, the infinite series, is going to have to diverge. So the infinite series diverges if the individual terms in that series don't go to zero. Now, I want us to be careful here. That is not saying, we are not saying that if the limit of the a sub n's is zero, then it converges. That's not a result. Sometimes when the limit of the a sub n's is zero, it'll converge. And sometimes when the limit of a sub n is equal to zero, the series diverges. So if the limit of the a sub n's is zero, then it could converge, it could diverge. But what we're saying is if it's not zero, then it has to diverge. So if the individual terms have limit that is not equal to zero, then this diverges. And what that allows us to do now is skip the calculations of the partial sums on a series like this. We could just say, oh, I can see that the individual terms never go to zero, and therefore the sum of this has to be diverging. And that skips a lot of work. So we can skip a lot of work by using some shortcut rules. And that first shortcut rule is this divergence rule. To notice that if the individual terms in the infinite series don't go to zero, then it has no hope of converging. Therefore, the infinite series diverges. Now, we'll look at some other shortcut rules as we go on, and we're going to develop some other shortcut rules for determining when a series diverges and when a series converges. Because I don't want to always be stuck with dealing with the partial sums. Now, before we develop lots of other shortcut rules, we're going to have to kind of see some of these. What I'm going to do is give a few examples that are types of series, and we'll develop some shortcut rules for some of these different types of series. So let's take a look at the infinite series of when we take 1 over n minus 1 over n plus 2. This is called a telescoping series, and you'll see why in just a moment. All right, so let's go ahead and do the first part. I'm going to write the first partial sum, and basically I'm not going to write all these terms because I'll write them down here in the partial sums. So when I plug in n equals 1, I get 1 over 1 minus 1/3. When I plug in n equals 2, well, first off, with my partial sum, my second partial sum, I get the first term, which I already have established, and then plus the second term is 1/2 minus 1/4. The third term, something interesting happens. We get 1 over 1 minus 1 over 3 plus my second term, which is 1/2 minus a fourth. And then in my third term, I get 1/3 minus 1/5. And what you'll notice, and this is why it's called telescoping, is that this negative 1/3 up front can cancel out with this 1/3 in the third term. And what we'll get is we'll get 1 over 1 plus 1 over 2 minus 1/4 minus 1/5. That's the third partial sum. Now, when we do the fourth partial sum, we're going to start out with the exact same idea, with the exact same first three terms. Whoops, thought I copied that. Actually, let me just start it out with this. We'll start out with this. That's the sum of the first three terms. And then we'll add a fourth term, which is going to be 1/4 minus 1/6. Notice this positive 1/4 is going to cancel out with this negative 1/4. And so I'm going to get 1 over 1 plus 1/2 minus a fifth minus a sixth. Notice that was the pattern here. We had 1 over 1, if I rewrite this, plus 1/2 minus a third minus a fourth. And then in the third term, it's minus a fourth minus a fifth instead. In the fourth term, I got minus a fifth minus a sixth. Well, see, in the fifth term, I'm going to take this result, that's the sum of the first four terms, and then add 1/5 and then subtract 1/7. The minus 1/5 and the plus 1/5 are going to cancel each other out. So that's what you get for the fifth term. And in the sixth term, you take these, you take the sum of the first five, and then you'd add 1/6 and subtract 1/8. And obviously the reason why it's called telescoping is because each time we're adding another term, a lot of the terms are canceling each other out. So envision some old-time sailor with a telescope and they pull it out and extend it the length and then can push it and contract it back in. Well, this is the contracting back in part, pushing it back in. For the seventh term, I'm going to get 1 over 1. I won't even, you'll see the pattern. We see the pattern here. 1 over 1 plus 1/2. I'm going to get minus 1/8 and then minus 1/9 when things are telescoped. So my S sub n is always 1 plus a half and then minus 1 over this would be n plus 1, and then minus 1 over n plus 2. So we get 1.5 minus 1 over n plus 1 minus 1 over n plus 2. Now, this is a really nice sequence of numbers. These partial sums are a really nice sequence of numbers. We go here. The limit of a constant number is just that constant number. The limit as n goes to infinity of 1 over n plus 1, as the denominator grows, this fraction goes to 0. As this denominator grows, this fraction also goes to 0. So I get basically 1.5 minus 0 minus 0 as n goes to infinity. So this telescoping series converges to 1.5. Again, it's being called telescoping because there's so many terms that are canceling each other out. So many pieces of terms that cancel each other out. Now, there's no like good formal way of coming up with a summation for a telescoping series, but you can see that if we are in this situation, then that this type of telescoping series converges. And I say this type because obviously there might be another type that diverges. And there's no real good geometrical visualization of this. Well, there may be a geometric visualization, but not one for this class. Now, let's take a look at this series. Let's do this example 4, and we'll find the first few partial sums of 7 times 1/4 to the nth power. This is called a geometric series because each of these terms this is like an exponential function. Each term is given to me by an exponential function, and in that case, the series is called geometric series. So geometric series means we're summing up terms that are given by an exponential function. Now, the first thing to notice here is that normally in an infinite series, we start our count with n equals 1, but we can actually start our count with n equals any other number. And in this geometric series, it's useful to start our count at n equals 0. And we'll see why that is in a little bit. But if I start my count at n equals 0, then I just say my s sub 0, that is the partial sum when n is equal to 0, is going to be 7 times 1/4 to the 0th power. That's just going to be a 7. S, so again, when I plug in 0, 1/4 to the 0th power just becomes 1, and I get a 7. When I plug in both my n equals 0 and my n equals 1 term, I'll get 7 times 1/4 to the 0th power plus 7 times 1/4 to the first power, which is going to be, here's how I'm going to write it. I'm going to factor out a 7, and then I'm going to add 1 plus 1/4. Now, as I do that, you could try to make that a fraction. I am going to just write it as a decimal. So that 1 plus 1/4 becomes 1.25. S sub 2 will be 7 times 1 plus 7 times a fourth plus 7 times, well, when I plug in a 2, I get 1/16. Once again, I'm going to factor out a 7. And I'm doing this because I kind of know where we're headed here. I can just add 1/16 to the 1.25 I got earlier and get a 1.3125. S sub 3, well, it'd be the sum of these terms, which I already know is 7 times 1.3125 plus 7 times what happens when I plug in a 3. 1/4 raised to the third power is 1/64. When I add those together, I get 7 times 1.32815. And I can keep going with this. These are not going to be nice fractions to deal with, so that's why I'm leaving them as decimals. And hopefully I can see the pattern with decimals that we're headed to. So basically S4 is S3, which we saw as right here. I'm just going to write it that way. Plus 7 times 1 over, oh, I'm sorry, I hit something. 1 over 256. And then S5 is going to be the S4 plus 7 times 1 over 1024. And then I'll do a couple more. S6 is going to be S5 plus 7 times 1 over 4096. And then we'll do one more. S7 is equal to the S sub 6 that we just found plus 7 times 1 over 16,384. Okay. Now, going back up and filling in what we have. So if we start with this, and then we add 7 times 1 over 256, we end up with 1.33, or sorry, 7 times 1.332 0.03125. That's why I didn't want to write too long. If then I add 7 times 1 over 1024, I end up with 7 times 1.3330078. It would be 25, but my calculator rounds it. Only rounds to 9 decimal places. Then add 1 over 4096 to this number. We're going to get 7.333. Oh, sorry, 7 times 1.333251953. And then when I take the 6th term, add 1 over 16,384 to the number inside parentheses. That means my 7th term is going to be 7 times 1.3333 12988. Again, these are all rounded to 9 decimal places. Now, there's no good fractional pattern for S of n here. But hopefully you can see that this is getting closer and closer to 1.3 repeating. So just based off of what we see in the decimal version, while we don't have a great fractional pattern that I can write as my S sub n, I can still say the limit of S sub n looks like it's going towards 7 times 1.3 repeating. Now, 1.3 repeating is 4/3. So the limit looks like it's going to 7 times 4/3. And that means this infinite series is going towards 7 times 4/3. Now, I'm writing it like that on purpose. Obviously, we can, by hand, multiply and get that that's 28 over 3. And if I wanted to, 28 over 3, I could call 9 1/3 or 9.3 repeating. But I'm leaving it like this purposefully. So there we go. Now, it turns out for a geometric series, obviously this took a minute to get all of these partial sums. So you might say, well, is there a better way? It turns out for a geometric series, there is a better way. For a geometric series, we're going to have a shortcut rule. And that shortcut rule is called the geometric series test. If our infinite summation starts our summation at 0 and goes to infinity, and we're summing up an exponential like function with base r, So we have a constant times r to the nth power. If r is between -1 and 1, then the individual terms in here are going to go to 0, and the geometric series is going to converge exactly to a divided by 1 minus r. If the r value is 1 or above in terms of absolute value, then the terms go off to infinity, and therefore the infinite summation diverges. We saw the limits of these types of things in a previous video, the terms anyways. And in that previous video, we said, oh, if we have limits of an exponential function, if our base is between -1 and 1, then the terms are going to have limit of 0. And if the base is above 1, then the terms are going to go off to infinity. If the base is below -1, then the terms alternate, and then they go off to infinity in absolute value. So this is the geometric series test. So our previous series had that exact form. And in our previous series, A would have been equal to 7. That's the constant. Notice that if I ever have a constant out front, I can just factor it out essentially. And then my R, for whatever reason, in a geometric series, they call the base R always. That's the traditional way of doing it. R is 1/4. Now this 1/4 is less than 1 in absolute value. So with the geometric series test, what I could have done is I could have said, since we're starting our count at 0 and going towards infinity, I know this is going to look like A over 1 minus R. I know it's going to converge because my base is less than 1. A over 1 minus R in this case is going to be 7 divided by 1 minus 1/4, which is equal to 7 divided by 3/4. And dividing by 3/4 is the same thing as multiplying by 4/3. So dividing by 3/4 is like 7 times 4/3. Notice how this is quite a bit quicker than trying to list out a bunch of partial sums. And with 4/3, 4/3 was a pretty recognizable decimal, but there are certain other ones that might not be as easy to recognize in the decimal version. So this shortcut rule with geometric series really helps us out. It allows us to do convergence and divergence of a geometric series very quickly. And there it is. That's the geometric series test. Now, you may ask where this comes from. Like, what in the world is this doing? How are we getting this infinite summation is equal to A over 1 minus R? Well, obviously the a can be factored out of the infinite sum just because we can factor out any constant times things. Um, how do we get a over 1 minus r here? How do we know that this diverges? Well, it turns out that this is just a consequence of dividing polynomials. Let me show you what I mean by that. So let's do this. Basically, let's take a polynomial like x squared plus x plus 1. Oh, that's not going to work. So x squared plus x plus 1 and divide it by x minus 1. All right. If I do that, then, oh, excuse me. Excuse me. I misdid that. I went that way. I want to do this way. So x squared minus 1 divided by x minus 1 gives me x plus 1. And if I take x to the third minus 1 and I divide that whole thing by x minus 1, then what I get is I get x squared plus x plus 1. And if I do the same thing, but I take x to the fourth minus 1 in my numerator, then what I end up with is x to the third plus x squared plus x plus 1. Notice what this is. This is a sum of x to the 0 plus x squared plus x to the third. So in general, if I have some summation, let's actually get a summation. Let's say I go from n equals 1 to 16 of x to the nth power. Then what I would do is that would be this right-hand side, x to the 16th plus x to the 15th plus x to the 14th, all the way down till I get x to the first and then x to the 0th. Actually, let me start my count at 0. So I get the plus 1. So to get the plus 1, we have to start our count at 0. Then this thing on the right becomes equal to x to the 16th minus 1 divided by x minus 1. So this sum becomes the fraction x to the 16th minus 1 divided by x minus 1. What's going to happen when I do a limit as that n goes to infinity? Well, I'm going to get x to the nth minus 1 times limit as n goes to infinity of that expression, of this expression here. Now, if this x is going to be a numerical value, if x is bigger than 1, then x to the n shoots off to infinity. If x is less than 1, then x to the n goes to 0. So let's, instead of using the x, let's just use the letter r so that we're consistent with our geometric property. So if absolute value of r is less than 1, then r to the nth power is going to go to 0. So this summation is going to be equal to 0 minus 1 over r minus 1. Now, if I want to make this a positive 1 on top, I can multiply times negative on bottom, negative on top. That is going to be 1 over 1 minus r. And then if I multiply the whole thing by a coefficient of a, then just a gets multiplied on the top. So if I multiply by a coefficient of a, then I just get that or that. So if r is less than 1, this thing goes to 0. If r is greater than 1, then that thing goes out to infinity. Then this r to the n here goes off to infinity. Actually, technically, if r is a negative, then it bounces back and forth between really big numbers and really small numbers. So really big negative numbers, really big positive numbers. So if r is greater than or equal to 1, then that summation diverges. And it's all basically just this equation that when you sum up x to the 0 plus x to the first plus x to the second, you can write it as this fraction. When you sum up x to the 0 plus x to the first plus x to the second plus x to the third, you can write it as this fraction. So when you sum up from n equals 0 to infinity, you can write it as the limit of that fraction. And then r to the n is either going to go away if r is less than 1, or it's going to go off to infinity if r is greater than 1. So that's where the geometric series rule comes from. Once we know this geometric series test, then if I'm given a geometric series, I can skip all of my partial sums, and I can very quickly determine if the geometric series converges or diverges. And if it does converge, I can determine what it converges to. So let's take a look at another example. We're going to find the convergence of this series, which is a geometric series, and we'll determine what it converges to if it does converge using the geometric series test. Now we're going to do this example, and so I don't have to go back. I just want to show you that we'll do another example as well, and we'll start our count at 1. So we'll start our count at 0, like the geometric series test does, and then we'll start our count at 1, and I'll show you how to determine how to do that as well. So again, geometric series test, my summation has to always start at 0 if I want to use the a over 1 minus r formula. So let's go ahead and do that. So this is a geometric series, and this is a geometric series with A equals 5 and R equals 2 over 9, or 2/9. That R is less than 1 in absolute value. So I know that this series is going to converge, and it's going to converge to A over 1 minus R. Since I'm starting my count at 0, this series is equal to A over 1 minus R. Again, that's because this R is between -1 and 1. So in this case, that's going to be 5 over 1 minus 2/9, which is equal to 5 over the fraction 7/9. And again, if we're doing 5 divided by 7/9, you could think of that as 5 times 9 over 7. That would be probably a hard decimal to recognize for most people. But in any case, 45 over 7 is our final answer. If I want an approximate answer, I just type that into my calculator. 45 over 7 becomes about 6.43. So there you go. The series converges to 45 over 7. Now, what about starting our count at 1 instead? Well, think about this. If I start my count at 0, I'm getting a 0th term, and then I'm getting all of the rest. In other words, starting my count at 0 gives me 5 times 2/9 raised to the 0th power plus all the other terms. And all of the other terms is going to be a summation starting at 1 and going to infinity. So what I can do if I want to find the summation starting at 1 is I can start by finding the summation when n is equal to 0. We know already that that's 45 over 7. And then just subtract this first term. In other words, the left-hand side of this equation I know is 45 over 7. I know 45 over 7 is equal to 5 times 2/9 to the 0 is just 5, plus my summation starting my count at 1. If I subtract 5 from both sides, take 45 over 7 minus 5, that gives you 10/7 or 1 3/7. And now I know. Now I know that this summation, again, subtract 5 from both sides of the equation, is equal to 10/7. So basically, if we start our count at anything other than 0, then I begin by calculating what the summation is at n equals 0, and then I lop off this first term. If I started my count, if I was looking for n equals 2, then I could lop off the first two terms. I could lop off when I plug in n equals 0, and then lop off when I plug in n equals 1. But there you go. That's the whole thing there. So starting our count at 1, you get 10/7. Starting our count at 0, we get 45/7. And that's way, way quicker than utilizing the partial sums. And it's a lot easier to see. Let's try example 6 as well. We're going to take an infinite series that's of the form 1 over 2 to the n. We'll start our count at 0. By the way, this is the one we started out with if I took n equals 1. So this is exactly the same infinite series as what we had in example 1, except now I'm starting my count at 0. So I want you to try that one. And then what would happen if I took an infinite series, but I started my count with n equals 2? We already know what happens with n equals 1, so I figured let's use n equals 2 and n equals 0 here. I'll give a couple of seconds if you want to push pause. After that, I'll do it on my own. Now, this is a geometric series because if I wanted to, I could have rewrote this. Instead of as 1 over 2 to the n, I could think of this as the fraction 1/2 raised to the nth power, because 1 raised to the nth power is just 1, 2 raised to the nth power is obviously 2 to the nth power. So by rewriting this infinite series, it looks exactly like the geometric series. So this is a geometric series, and the a here, the coefficient out front, is just the number 1. The r is going to be 1/2. This geometric series converges because r is between -1 and 1. Anytime r is between -1 and 1, it converges. And therefore, since I'm starting my count at 0, starting our count at 0, again, a over 1 minus r gives me 1 over 1 minus 1/2. You can do the calculations on your own. You'll get a 2. So this geometric series converges to 2. If I start my count at n equals 1, then all I do is say, starting my count at n equals 1. Well, let me actually do it on the other side. When I plug in 0, I get 1 over 2 to the 0th power, which is 1 over 1, plus an infinite sum. So that's what we get, our infinite sum when we go from 0 to infinity, which means the infinite sum starting my count at 1 plus 1 should be equal to 2. If I subtract 1 from both sides, you'll see I got the same result that I got in the very first problem in this section. So the very first video, I got this infinite sum being 1 using partial fractions. Now, if I want to start my count at 2, then I'm going to take the first term, the one where I plug in n equals 0, and then the term when I plug in n equals 1. If I plug in n equals 1, I get 1/2. So if I start my summation at n equals 2, then the summation from n equals 0 is just lop off the term where we plug in 0, lop off the term where we plug in 1. This is going to be 1.5 plus the infinite summation is equal to 2. Then subtract 1.5 from both sides. I end up getting that if I start my count at 2, this infinite series converges to 1/2. Now, there are formulas where you figure out what happens when you start at n equals 1, what happens when you start at n equals 2. There are like shorthand formulas for that, but I typically don't use those. I typically just remember that the geometric series is test always works when you start your count at 0. And if you start your count at any other number, then just use the n equals 0 and lop off the first term or the first couple of terms it, to get the sum starting at any other value. So starting at 0, the infinite series adds to 2. If we started our count at n equals 2, then the infinite series adds to 1/2. Again, the infinite series, if you start at 1, adds to 1. We saw that earlier, and that's consistent with what we have here as well. Let's do one more example. Again, if you want to try this on your own, you can push pause on the video. In a couple of seconds, I will do the problem on the video. So for this one, we have an infinite series that is 5 times 1.2 to the nth power. The summation starts at 0 and goes to infinity. This is a geometric series. It has the form that we want. Now the a here is 5. The r is 1.2. That's really all we need to know. Therefore, because this r is bigger than 1, the series, the infinite series, diverges. And that's all we have to do. We say, hey, the R is bigger than 1, therefore the terms are going to grow. And if you wrote out the first few terms, they just get bigger and bigger and bigger. So it just keeps growing and growing and growing. Adding those up, we're going to add infinity basically. And so the thing diverges. So this infinite series diverges. By the way, you get a really interesting thing if you mistakenly just throw in the formula a over 1 minus r. If I actually calculated a over 1 minus r, what you would get is 5 over 1 minus 1.2, which is 5 over a negative zero point 0.2. And so you get a negative number that is specifically negative 25, which shouldn't make sense because you're adding up a bunch of positive numbers and it's adding up to a negative number. Again, that wouldn't make sense. So, anyways, some people will mistakenly do that, will mistakenly just say, oh, it's geometric, so let's do a over 1 minus r, and they'll forget to check whether that r is less than 1 or greater than 1 in absolute value. And if you forget to check that, obviously you can get some really strange looking results. But since r is bigger than 1, this geometric series diverges. Now, I want to point something out. We, in the last few examples, have been exclusively focusing on geometric series. However, don't think that every series that you're given is going to be a geometric series. There are lots and lots of different types of series, and we'll look at those in some of the next videos that we do. There's geometric series that we've seen. There's telescoping series. We saw that type. There's also things called a P series. There's constant series. Constant series are like the one where we're just adding up zero point 0.4 infinitely many times. There's things called alternating series. And there's a lot of different series that are just combinations of different types of series. So they're unnamed or they're complicated. So there's lots and lots and lots of types of series. We obviously have a really nice rule for the geometric series. And our goal in some of the next few sections is going to be to determine when series converge and when series diverge. We've already seen that for the geometric series, but we'll also look at that for P series, for constants. Well, we know what happens with constant series, for alternating series, etc., etc. So the goal will be to determine which series converge and which series diverge. And again, we have a really nice rule for geometric. We may ask, what are some other rules that we can use for infinite series? Well, one of the rules that we kind of hinted at with geometric, but actually works for any series, is what we call the constant multiple rule. If I have a series that converges to L. Then if I take each individual term and multiply it by a constant of C, then that new infinite series will converge to C times L, where C is again just some real number. So that's the constant multiple rule. That's pretty obvious that we can just sort of factor out a constant from a summation. Another rule that we can use is what we call the sum difference rule. If we have two series, one which converges to L and another which converges to K, if we create a new series with a sum of the two terms or a difference of the two terms, then that new series is going to converge to either the sum of L and K or the difference of L and K, depending on if it's the sum or difference of the terms. So if we add up the two terms, then we can, if we're essentially adding up the two series, then the series that I create is going to converge to L plus K. This allows us to use and break down infinite series into smaller pieces if I can. Now, by the way, this is only if we have real numbers that these two things converge to, that these two original things converge to. If one of them converges, or if they both converge to infinity, then, or excuse me, I misspoke. If both of these go off to infinity, then all bets are off. So this only works if my two original series converge to real numbers. If the two original series diverge, then this doesn't always work. The constant multiple rule will pretty much work if you think of L as infinity. The sum difference will not always work. So let's do this example using what we learned earlier and my constant multiple rule and my sum difference rule. We want to find if this series, summation starting at 0 going to infinity, of 6 over 2 to the n plus 5 times 2/9 to the n will converge or diverge, and what it would converge or diverge to. So this infinite series looks like we're summing up two different types of terms. So what we're going to do is we're going to use our sum difference rule and say that one infinite series is like taking a sum of two different infinite series, one where I use the first term and the other where I use the second term. That's my sum difference rule. If these two individually sum up to something, then I can apply this rule. If they don't, if they go off to infinity, then I can assume that the whole thing, the whole sum is going to go off to infinity if they add up to infinity. Now on this first one, we have 6 over 2 to the n. That's very similar to something that I saw earlier. In an earlier example, did an infinite sum of 1 over 2 to the n. but 6 is just a constant. So using that constant multiple rule, I can just say this summation, this first summation, is going to be the exact same as 6 times the infinite series of 1 over 2 to the n. And this second series is something that I've already found the sum of. So if I look back to what we've done earlier, I saved these. The infinite sum starting at n equals 0 and going to infinity of 5 times 2/9 to the n was 45 over 7. And the infinite sum starting at 0 going to infinity of 1 over 2 to the n was 2. So this second infinite series, I know, adds up to 45 over 7. And the first one is going to be, well, this is going to be 6 times the infinite series, which adds up to 2, or converges to 2. So that's simply going to be 6 times 2 plus 45 over 7, which is 18 and 3/7. So that means my original series converges to 18 and 3/7. That is, this original series converges to 18 and 3/7. So that's how we can use the sum rule, and that's how we can use the constant multiple rule. So if I already know an infinite series converges, and that infinite series is just a constant times one I know, I'm good to go. If I'm adding up multiple terms and I know the infinite series of each term, then again, we're good to go. By the way, these rules work. If these two rules work, a lot of times people try to write other rules that don't work. They'll write multiplication in here instead of summing and adding, and multiplication does not work with this type of rule. If I took a sub n times b sub n and added those up, it's not equal to L times k. So multiplication does not work unless that multiplication is by a constant number. But if it's a multiplication of series times series, it does not work. So be careful about that. This only works when we're adding the terms up or subtracting the terms. Does not work when I'm multiplying the terms. Again, the one exception that is if I have a constant which I can factor out. But a sub n times b sub n doesn't give me L times k when I add it up. So these two rules feel free to use to find infinite series when you can, but don't make up any other rules is what I'm saying. Now, there's a lot of times when the sums of infinite series can't actually, or not can't, but they're really hard to determine. A lot of times, however, we'll see in later sections that approximations can be made. In the geometric series test, We could actually calculate what the series converged to or whether it diverged. A lot of the next tests that we'll see in other sections will just tell me if it converges or diverges. And if it does converge, it might just be okay to have an approximation rather than having a specific answer. We got the specific answer in the geometric series, but not every series is going to have a specific answer that's easy to find. In fact, there's some well-known series, infinite series, that add up to some very unique values. These are not ones that you're going to have to know by any means, but you can kind of see some really unique things happening with infinite series. It turns out if you sum up 1 over n factorial and you start your count at 0, then you get the number e. That's the number of associated with natural growth, that 2.71828, et cetera number, which is really interesting. You add up a bunch of rational numbers and you end up with something that is irrational, as if we take an infinite sum of rational numbers. If you add up 1 over n squared from 1 to infinity, it turns out you get pi squared over 6. Again, it's pretty interesting that we're adding up a bunch of squares, 1 over squares, and we're ending up with a pi squared in the numerator. Obviously, again, adding up a bunch of rational numbers and ending up with something irrational that involves pi. Again, this may be this is probably fairly weird and surprising, but it's what it is. Here's some other ones. If I take -1 to the n plus 1 over n squared from n equals 1 to infinity, we get pi squared over 12. If I take an infinite sum from 0 to infinity of -1 to the n plus 1 over 2n plus 1, I get a pi over 4. If I take -1 to the n plus 1 over n summed up from 1 to infinity, I get the natural log of 2. Again, all of these are really interesting, weird numbers that we're getting. Some of these, again, have really nice explanations. There's actually a really nice explanation on YouTube of this pi squared over 6 or pi over 4, why we're ending up with pi here. But it was not made by me. So really weird sums that we can get. That's all I'm saying. You don't have to memorize these, but you do, we will see whether a lot of these series converge or diverge. Not these ones in particular. These ones obviously converge because we say they are doing that right now. So what I'm saying is, in the next few sections, we will look at lots of infinite series and determine whether or not they converge or diverge. And then with some of them, we can find an approximation. Not all of them, but so the big things in the next few sections will be, when does an infinite series converge or when does it diverge? We know that in the case of the geometric series. We also know that in the case of the divergence rule. And now we're going to move forward and say, well, what about with other types of series that don't fit the divergence rule and that are not geometric? So that ends this video. We'll take a look at those other infinite series in the next video.